Hello, everyone. My name is Ran Xu. I'm an infrastructure engineer of World Platform team in Line. Our team, together with network team and SRE team, are in charge of this Line private cloud platform. Over past 1 year, more and more Line core services are migrated to the private cloud platform. In that case, we faced the various challenges such as a scale issue, performance issue, and reliability issue. Today, I will talk about one reliability issues of the identity service we encountered inside the Line private cloud platform and share how we think about this issue and how we resolve it. So first of all, I would like to introduce myself. I joined the Line in September 2019. I was responsible for developing and maintaining the Line managed the Kubernetes service platform. And I'm also in charge of the reliability improvement work within my team. So here is the agenda of my topic today. First of all, I will introduce the architecture of Line private cloud platform. Second, I will also introduce the two actual outages of the identity services. Third, I will also share the analysis result of both outages. Finally, I will share how we improve our identity service. So now let's go to the architecture introduction of Line private cloud platform. So Verda is the Line private cloud platform, as I mentioned. It is responsible for providing reliable infrastructure services to Line developers at a low cost. Verda platform includes the two parts. First part is a user interface. Second part is a set of backend infrastructure services. For user interface part, we provided two types of interface. First one is RESTful API. Second one is Web UI. Through these API and Web UI, we expose backend infrastructure services to Line developers by hiding unnecessary technical details so that they can use them conveniently. For backend infrastructure services, it is separated by 3 layers. The first layer is IaaS layer. It provides the several fundamental IaaS services to Line developers, like load balancer, like block storage, and the VM. The second layer is the managed service layer. It provides the managed middleware services using the IaaS layer services. This service allows the Line developers to use those middlewares without having to know the details of each middleware, like Verda managed the Kubernetes service. The third layer is the PaaS service layer. It provides some platform services to Line developers, like function service and CI/CD pipeline. In the architecture graph, one of the most important services I want to highlight in here is identity service in the IaaS layer. In the Verda, we customized the Keystone, the OpenStack identity service to provide the API client authentication and the service discovery functionalities to Line developers. Almost all products that Verda provides also rely on it. As I mentioned, more and more Line developers start to deploy their services on Verda. More applications usually means much pressure on platform side. So in past 6 months, we encountered 2 big outages of the identity service, as I mentioned, inside the Verda platform. So now let me introduce what it is and what we learned from them. So I will introduce both of outages from the 4 perspectives as below: issue, impact, workaround, and root cause. So the first outage happened on March this year. In that time, the identity service, the Keystone service in our platform is down due to the malicious client request. The issue we encountered in that outage is Keystone service is stuck and it cannot handle any new request. includes the token issue and the token validation request normally. The impact is pretty huge, as I mentioned. Almost all where the infra services rely on the authentication functionality that Keystone service provides, right? So they cannot serve for line developers normally during the Keystone is done. Because of the serious impact, we try to restart the Keystone to recover this issue for avoid the further damage. Fortunately, it works. But it reminds us our Keystone service was in the high reliability risk, right? It may break all Vert infra services anytime, so that Vert cannot serve for our line developers. Once we confirmed that the service is recovered by the workaround we took, we start the investigation at once. For the root cause part, first of all, we record what is the expected behavior of handling the request in the Keystone side. And then we try to detect what is actual behavior and compare this expected behavior and actual behavior, and to find if there are any difference, so that we can locate the root cause based on it. So here is the expected request handling flow in the Keystone side. You can see here, a Keystone service usually includes the three parts. Apache Web Server, it is responsible for receiving the HTTP request from the line developers or another line infra services. The second part is pre-forked worker processes. It was pre-forked by Apache server after it started for handling Keystone HTTP request. Each worker runs the Keystone Whiskey server that is implemented by the Apache using the mode Whiskey library. The third part is the Keystone Whiskey applications. Each Keystone Whiskey server will run a Keystone Whiskey application. The Keystone uses the WebAuth package to make the Keystone business logic to be able to expose as a Whiskey application. So when the token validation or token issue request comes to the Keystone service, it will go to the Keystone Whiskey application through this flow and proceed as a corresponding token issue or token validation logic. The related response will be returned through this workflow in the reversed order. So that is the expected behavior I want to introduce about the Keystone request handling. So now let's check what is actual behavior. First, we checked the logs of Apache server. We found the request that caused the Keystone is stuck has some similar traits. First one is the value of content length is of the request body is greater than the actual size of the request content. Second one is each bad request is given up by Apache server after 20 seconds. The 20 seconds is the default read request body timeout settings in the Apache web server side. Here is the example of the logs of Apache server in our dev environment. You can see here the Apache server hit the timeout issue right after 20 seconds passed. Second, by checking the logs of the Keystone Whiskey application, we also found it always waits for the data inside the request body after it confirmed the expected content length. But as you know, no data is sent. So in that case, or no data is sent, or no enough data is sent. So in that case, one global level exception is posted in the Whiskey application side. And because this exception isn't handled well in the Keystone Whiskey application side, it causes that the whole Whiskey application is down. The corresponding exception is also shown in the Whiskey server side. Here is the logs we detected from the Whiskey server side. You can see here that exception was posted in the Whiskey application side, but it was propagated to the Whiskey server side. And it caused, and after that, we feel the root cause is more clear in our head for this outage. Because Apache used the mode Whiskey library to implement the Whiskey server, that pre-forked the several worker processes to load and start the Keystone Whiskey application. The default settings of the number of these worker processes is 3 in our dev environment. So each worker process in here cannot handle lots of requests at the same time. So when malicious request above, as I mentioned, come in, it caused the Whiskey application is done first, and it easy to make the 3 worker process are busy. The Keystone cannot handle any new request anymore, and it looks like home. That is why we think our workaround restart the Keystone service directly can recover this issue. Because when Whiskey server found the Whiskey application is down, it never restart it. So in that case, the further request cannot be handled by the Keystone Whiskey server normally. So now we got the root cause of this outage. So the second outage happened on May this year. The Keystone service in that time is down due to the request exceed the service processing capacity. The issue we encountered in this outage is similar with the previous one. The Keystone service cannot handle the token issue and the token validation request normally. The impact is also seen. Almost all Vert services cannot serve for the line developers normally. But the issue is a similar one, right? Similar with the previous one. For avoid the further damage, we try to recover this issue by previous workaround we took in the first outage, as I mentioned, restart the Keystone. But it doesn't work. It let us feel the current outage maybe is more complicated and the root cause is a little different. So before we took any workaround to recover this issue, we started the investigation work at once. As I mentioned, the issue in the malicious request that caused the previous Keystone outage is the content length is greater than the actual size of the request body. But in this outage, the root cause is related to the number of the concurrent requests arriving at the Keystone service at the same time. Here are some evidence we detected from the Grafana dashboard. We detected 3 points. The first one is 20.5 million requests come to the Keystone service during the 15 minutes time window. It means that the QPS of the Keystone service in that time is around 2,777 requests per second. Normally, for each authentication request, the API latency is 30 milliseconds. It means for each Keystone Whiskey app, the maximum QPS is 33 requests per second. So if each Keystone service forked the 12 worker processes to start the Keystone Whiskey server, the replica of the Keystone service is 3 in that time. It means the maximum number of the requests that Keystone service in our production environment can handle is 1,188 requests per second. But the current number of the requests already exceed this capacity of the Keystone service, right? And then we try to confirm that where those requests come from, because the current issue indicates there is the specific client sending a bunch of the requests to the Keystone service, but that is unexpected situation. We never got notified. So after we checked the audit log of the Keystone service, we found a huge number of authentication requests that come from the same client. It is a word managed the Kubernetes service, as I mentioned, in the managed service layer of a Lime private cloud platform. So now, root cause of the second outage is also clear. A large number of the token validation requests from the word managed the Kubernetes. It exceeds the handling ability of the Keystone service. So in that case, the request from another client cannot be handled normally. For the workaround, because of the serious impact of this issue, after we located the root cause, we deployed a totally new Keystone service and require members of VKS team to change the Keystone endpoint they are using. And the issue on the original Keystone is gone because the majority of the load of that Keystone service is distributed to another one, the new Keystone deployment workload we cloned, right? And another word infra services is also recovered in that time. By knowing the issue and the impact on the previous outages, there is no doubt we have to find a fundamental way to improve it, right? Because before we take any action, we want to analyze the previous outage first, so that we can identify what is the real problem behind of them. I will share our analysis result from the two perspectives. The first one is architecture, the second one is the dependence. So when we checked the request, the distribution situation of the Keystone service, two observations we got. First one is almost all requests that come to the Keystone service within the 15 minutes time window are related to the authentication. Authentication, I mentioned in this context, includes the two parts, token issue and token validation. Around 99.95% of the load on the Keystone service are token validation. Only 0.05% requests are the token issue. So the first observation indicates one fact to us. Authentication functionality of the Keystone service is the most used functionalities. But the authentication is just one of the functionalities that Keystone provides, right? As I mentioned, Keystone also provides the service discovery functionality to word infrastructure services. Then we also checked the patches of line customer Keystone code repo. We found that all patches we added to the Keystone are related to the special business logic that are only for line internally. Token issue business logic has never been updated more than 3 years right now. It lets us feel the authentication, the most important and the most used function of the Keystone service, is taking the unnecessary and extra reliability risk from our customer business logic. According to the second observation, we also found that the token validation is the most used feature compared to the token issue. So in that case, when token issue has something wrong, token validation shouldn't be affected. So after we identify the real problem behind of both of the outages, from the architecture perspective, it seems like the authentication logic is coupled with another customer business logic inside the Keystone side, and their life cycle is totally different. So in that case, what we would like to do is decouple them into the different Keystone deployment workloads. And one is only responsible for authentication. Another one is for the left functionalities. But even if we decouple the authentication and original Keystone service, it seems like the coupling issue also exists inside the authentication functionality. As I mentioned from the second observation, the token issue and the token validation still coupled together inside the same binary. But we want to keep decouple the token issue and the token validation idea in our mind first, because decouple a service into the too many microservices is not a good idea, due to it will increase the complexity of service management. So before we find another strong reason, we don't want to make that decision easily. So from the dependence perspective, one dependency issues we also found, that is that all components inside the Verda line private cloud platform depend on the Keystone service. Once Keystone service is down, it causes that another component are also down. Although make each services inside our platform independent completely is impossible. But it doesn't mean we should stop in here. Any little improvement for reducing the unnecessary dependency between the different services is valuable. Because we already knew the token validation is the most used feature by another infrastructure services. If we can move the token validation work from the server side, I mean Keystone side, to the edge client side, we could reduce the huge part of the unnecessary dependency stuff between the infra services and the Keystone services. After that, the token validation load of the Keystone service will also be decreased dramatically, because the client will never access the Keystone service for token validation stuff, right? So after we finalized the improvement idea from the architecture perspective and the dependence perspective, let me share with you how we make it happen one by one. First improvement we want to do is decouple authentication functionality from the Keystone service. Before we did any actual work, let's see how the Keystone is deployed currently in the Verda. Keystone itself is deployed using the deployment workload. Necessary configuration of the Keystone, like Apache server configuration, is stored in the config map and encrypted secret resource. In front of the Keystone deployment, you can see here the Kubernetes service and ingress controller are located in here. Besides, there is the load balancer component that is deployed in front of ingress controller. So when the request comes to the Keystone service, it will go through the load balancer, ingress controller. Then ingress controller will distribute the request based on the API path on the L7 layer to the Keystone Kubernetes service. Finally, it will go to one of the Keystone pod. According to the current architecture, the decouple work can be separated into the two phases in our mind. In the first phase, we can clone a totally new Keystone service that only served for the authentication request. Then creating a corresponding Kubernetes service of the new deployment for load balance request to each backend Keystone pod. Finally, we can add a rule in the ingress source side, distribute the authentication request whose API path prefix is v3/auth to the new Keystone service. In the second phase, of course, we can remove the unnecessary logic in the new Keystone services, except the authentication, right? Not only decouple them from the architecture perspective, but also from the implementation perspective. But from the reducing the serious impact of the Keystone outage side, we prefer to proceed the first phase first. For the second phase, that is not urgent right now. We can plan it in the near future. After first phase is finished, the architecture should be like below. The authentication request will be forwarded to the new Keystone deployment. Another request will be forwarded to the original one. So that's all what we did for the first improvement. The second improvement we would like to do is moving the token validation stuff on the edit side and re-implement it in the stateless way. So if we want to re-implement this Keystone token validation in a stateless way on the edit side, we should know how a token of the Keystone is generated and how it is validated first. So in our environment, the Keystone uses the Fernet token as a token provider. So the below explanation are also focused on the Fernet token. One Fernet token generation needs the several things. But two of them are pretty important. First one is a ciphertext. It is a combination of the token issue payload and some padding characters. As you know, when you want to issue a token in the Keystone side, you need to give some arguments in the request body, like which scope you want to apply this token and which domain you want to apply for this token, right? The second part is the Fernet key. You don't need to know too much about the Fernet key in here. Just understand it as a general private key that is usually used in the encryption and the decryption area. The Keystone will encrypt this token payload with the Fernet key and combine with another part, as I showed in this graph. Sign it with the HMAC key. HMAC key is another kind of the private key. Of course, you also can understand it like a previous way we understand the Fernet key, right? And then we got the one Fernet token. That is how a token is generated in the Keystone side. For the token validation part, let's see the request payload of the token validation first. You can see here, after the Keystone receives this request, first it will use the Fernet key to decrypt the token that is in the X subject token HTTP header. And then it will compare the expired time of this token with the current time step. If it is already expired, Keystone will return error about the token not found to indicate to the client, okay, this token is already invalid. The third, it will check if the token is already revoked. If it is, it will also return an error about the token not found. And otherwise, it will return the identity info related to this token, like scope, domain, and expired time to clients. After we knew how token issue and the token validation work, let's talk about how we improve the token validation. If you recall the token validation process, the key point, one of the key point is the Fernet key, right? Because after we decrypt that token, we can get some info to do the token validation stuff. Once we can get this Fernet key and decrypt the payload, all we need to do is just checking they are already expired or not. So if we can make the token validation as a stateless and do it on the edit side, we should store this frontend key in a safe place, and it can be shared with the Keystone and another client. Because we already deployed the Keystone in our internal Kubernetes cluster, the most direct way of sharing this frontend key is storing it to the encrypted secret resource. The private key that is used for encrypting this frontend key will be rotated periodically. It is pretty easy to do, but there is a second thing we also need to handle, where we should inject this token validation logic into the client side without intrusion of the client implementation. Actually, inside the Verda, lots of Verda infra services is deployed with the CloudNative proxy component that is called Verda Common Proxy as a sidecar container. It is responsible for providing the Verda Common Proxy functionalities to each Verda infra service in the form of plugins, such as API schema validation, audit logging, and access control. It does part of works that the service mesh component did, like is2 and linkerd. So according to this component, we already had inside the Verda platform. For the token validation feature, it is also one of the common logic that is needed by each Verda infra service, right? In that case, the Verda Common Proxy is a good place to implement the token validation as a middleware of the pipeline of a request handling process. You can see here, we can inject the token validation logic as a middleware of the pipeline of the API request handling process. In that case, we don't need to require any client code changes. We just change our sidecar container, but that is expected. That is one of the purpose we want to have this common, the proxy sidecar container, right? We want to aggregate the common business logic from the proxy functionality perspective into the individual, the container. So here is the desired workflow of a stateless token validation in the Verda Common Proxy side. You can see here, once two improvements are planned are introduced, we can release the original Keystone service that includes our business logic anytime without affecting the authentication functionalities in the left side of this graph. The authentication logic will not be coupled with another logic. In the middle of this graph, you can see here, the Keystone service for the authentication purpose will have its own, the life cycle. The second improvement we can got is each Verda infra service can do the stateless token validation work in the Verda Common Proxy side without sending any request to the Keystone service. That is pretty good from our perspective, right? Because there is no any dependency between the client and the Keystone service for the token validation perspective. And the token validation is the majority of the request that Keystone is handled. So in that case, the load of that Keystone service will be decreased dramatically. So it means after this architecture is introduced to our identity service, even if original Keystone service API, in the right side of this graph is down, the token validation and the issue still can work. And even if the original Keystone for the token issue is down, the token validation will also work. And when the token validation load increased, by adding some new word infra services, I mean the number of the client is increased. That token validation load handling naturally scaled out together with the client, right? Because the token validation part right now is done inside the client side. The number of the client is the number of the component that is responsible for handling the token validation. That is pretty good. We don't need to care about too much things on the scale out side, right? When the number of the client for the token validation is increased dramatically. And when the Keystone release and the operation got the issue, I mean the original Keystone, the Keystone service for the token issue will also not be affected by it. So that's all we want to. That's the expected situation we want to achieve after two improvements from the dependence perspective and architecture perspective we introduced. So that's all I would want to share with you about our improvements of the identity service. So thanks for your listening. Yeah, thanks.